All right, welcome to another exciting episode here, Spain Park AP Chemistry. Today is Monday, September the 29th. We're almost finished September, almost finished the first 9 weeks. Woohoo, almost there. In reality, remember, we only do about 3.5 9 weeks for this class. We're done at the beginning of May, so time's flying. We gotta get our proverbial rear in gear. Let's get going. Okay, so Jonathan, what are they supposed to do if they're liking these videos?
Supposed to hit that like, smash that subscribe button, and ring that bell.
That's what you're supposed to do.
Yeah.
Okay, let's see if we can get my subscriptions up to 220, 250.
220K?
No, I wish. I'm not be making money. Okay. So who would like to answer? What are the steps? What do we need to do? First off, what do we need to do in order to be able to do number one? What's the first thing that we need to know we need to know?
The volume of the stock solution.
The volume of the stock solution that's needed, correct? And how do I find that, Nash?
What's it called? Dilution ratio thing.
Okay, which is what?
MC times BC equals MD times BD.
Perfect.
Man, that's some great stuff right there.
Okay, so what is the molarity of the concentrated?
0.5.
Try again.
12.0.
The concentrated. Which one is a bigger number? That number or this number?
This number.
12 is bigger than 0.5. Therefore, 12 is the concentrated, 0.5 is the dilute. So we're going to go with 12 molar. And again, what's the question, Nash? What do we need to find?
The volume of the stock solution.
Which would be the concentrated. The volume, that's my unknown, is equal to the molarity of the dilute, 0.5 molar, times the volume, how much we want to make. Now, do I need to change that to liters?
No, because it's a ratio.
It's a ratio, so if I leave it in milliliters, what's the volume answer going to come out into? Milliliters. Okay, so it's going to be times 250 milliliters. So the volume of the concentrated is equal to what?
10 milliliters.
Okay, so we divide this by 12, and we get 2 sig figs, so 10 milliliters. Do we agree with that?
Yeah.
Yes.
Okay, so then what do we go? Let Nash, I'm going to stick with you. What do we do next?
So you get like a graduated cylinder,
Okay,
and you put 240 milliliters of water into the cylinder, and then you put the stock solution in the cylinder.
okay, close. Okay, because you did right, because you want to have the water, and you want to add the acid to the water. Okay, but do we add 10 and 240? Okay, do the volumes always add up directly?
No, because it can mix in.
Okay, they can mix in. Okay, number 2, do I want to use a graduated cylinder as my final?
With the volumetric.
I want to use a volumetric flask, okay, for my 250. So what I would, somebody else, let's talk about what would be a better procedure, okay? And actually, I would give you the option on this one, since it was 10 milliliters, I'd give you a smaller graduated cylinder. So what could we do? Along the same lines, but instead of using the graduated cylinder, first off, a 250 milliliter graduated cylinder is going to be, they do make them, but they're not as common, okay? But using your volumetric flask, how could we do this?
Put the water in first.
How much water?
At least 240.
I would just, again, what you're going to say is about 2/3 full. You don't even have to be exact on this. Fill the volumetric flask about 2/3 full, and you would always want to say with distilled water. Okay? Then what? Okay, so you have to measure the 10 milliliters of HCl. Now the reality is, if this were an AP test, they're going to give you a 10 milliliter pipette. This is going to be a more accurate way to deliver. This is a 25, but they make a 10. And you would use a 10 milliliter pipette to deliver 10 milliliters to your flask. So a pipette is the most accurate way to deliver, it's because it came out to exactly 10. if it wasn't 10, which, you know, it was, let's say it was 9.5 or 8.5, that's when you're gonna wanna use a graduated cylinder. Okay, but because it was exactly 10, you could use a pipette, okay? This is, I'm just trying to let you, this is the most accurate. Okay, but let's just say, we'll use the graduated cylinder, fill it up, measure 10, pour it into here, then what?
You want to shake it.
Where you can just swirl it to mix, then add the water to the line. Okay, put a cap on it and mix. So now we have 250 milliliters of 0.5 molar. Okay, so we know we're gonna use this. Okay, figure out 10 milliliters, use a volumetric flask for the 250, it's the most accurate. Fill it partially full with water, add the acid to the water, fill it up the rest of the way. Mix thoroughly. And you don't even have to put a say, you just mix thoroughly. All right. What was it? I didn't. Then you did 3. Number 4. What number was next? 4 was next. Okay. Assume 6.73 grams of sodium carbonate is enough water. Notice that it says dissolved in enough water to make 250. Okay. You're not adding 250. That's when we're always making a solution. You add the solid. You add enough water to bring it up to. So again, on this one, you would make the solution. You would put the 6.73 grams into here. Okay. Then you can fill it 2/3 of the full of water. Swirl it. Okay. Get it to dissolve, and then add the water up to the line, and then mix thoroughly. Okay. What is the molarity of this solution? So molarity is equal to moles per liter, which is going to equal grams over molar mass over liters. So I take 6.73 grams. What's the molar mass of the sodium carbonate? 105.99. Do we agree with that number? If you said 106, that's fine. 105.99 grams per mole. Divided by my liters, which is 0.250. And what's my molarity come out to?
0.065.
0.
Wait, molarity.
Molarity.
0.254, yeah.
Okay, now you guys are snapping.
Molarity.
Okay, so that's part A. So part B though is, what are my Na plus and CO3? Well, what is sodium carbonate when you put it into water? What's it going to dissociate into?
2 Na plus.
2 Na pluses.
And then the CO2 2 minus.
Okay? So if I have 0.254 molar is what I made, none of it's going to dissolve like this. Ionic compounds 100% ionized. They never dissolve like this, they always dissolve as ions. But for every one of these, how many sodiums do I get?
2.
So what's the concentration going to be in my Na plus?
0.508.
No, it's not going to be half, it's going to be twice. For every one, we're going to get 2. Right? If I have 10 markers, but anytime I put the marker into water, it breaks up, the caps come off. And I get 2 caps for every marker. So when I put in 10 of these pens, I'm going to get 10 pens, but I'm going to get 20 caps. This is going to break up into 2 caps for every marker, right? So if I put in 10 of these, I'm going to end up with 20 caps and 10 pens. So if I put in 0.254, again, if I put in 10 of these, I'm going to end up getting 20 of these and 10 of those. If I put in 0.254, I'm going to get 0.508 and 0.254 molar of that. Do y'all see that? It's just gonna be, and if you wanted to do it mathematically with units, you could say 0.254 molar Na2CO3 times 2 moles of Na plus for every 1 mole Na2CO3, if you want to do it mathematically. Okay? It's important to kind of know, this kind of goes along with that highly missed question of which is going to give you the most particles when it's dissolved in water.
But how is the Na2CO3 0.254 molar, but then the right side has more than that? How does that?
Because it's breaking up into smaller pieces.
Would that not? How would that work with the law of conservation of mass? If they're two different.
Moles is not an amount, moles is total number of particles. Okay? So if I take a dozen donuts, but I cut them in half, how many pieces do I have now?
24.
Do I still have this law of conservation of mass still holding true? But you have smaller pieces. You just have more of them now. Same thing is true here, is I'm in smaller pieces, I got more of them. So I got, for every 1 particle that I put in, it's breaking up into 3, so I have 3 times as many particles dissolved. So I have this and this, when you add these two together, it's 3 times of that. Because it broke, for every 1, it broke into 3. So I am still conserving, it's just smaller pieces. Now, if we were to do the grams, how many grams do we have here and how many grams do we have there, it's gonna be the same number of grams. So we still have 2 sodiums and 1 carbonate, 2 sodiums and 1 carbonate.
Why is there like a designation on like the molar, like 0.508 molar, because that's not the same thing as 0.254 molar. You know, like, so if you're saying that they're just smaller and there's more of them, how do we tell the difference between 0.25 molar?
Because we say 0.25 molar sodium carbonate versus 0.508 molar Na plus. When you label it as the Na plus, that's telling me that it's the smaller particle. Okay? And that's why ionic compounds, so it's really gonna be the ion concentration that's gonna be the most important, not how much of this we put in, because it's never gonna dissolve like this, it always dissolves like that. All right. I don't know, I still feel like there's some cloudiness there, but we'll work through it. All right, so let's turn the page. Golly, time flies when we're having fun.
Whoa.
What is the mass in grams of 250 milliliters of 0.0125 molar? Now, is this a chemical reaction? No. So it's just going to be molarity again, right? Yeah. Okay. So this time, if molarity is equal to grams over molar mass over liters, how do I solve for grams? Okay. I think I heard, you guys don't talk loud enough for an old man. Liters times molar mass times, liters times molarity times molar mass. I'm going to multiply both sides by liters, and that's going to leave me grams over molar mass, and multiply both sides by molar mass. So now, to get grams, so I'm going to say liters is 0.250, I do need to change it to liters, times my molarity, which is 0.125, and always, for units purposes, moles per liter, times my grams per mole. What's the molarity that came in for? I mean the molar mass.
Molar mass.
158.04.
158.04 grams over 1 mole. So notice that moles cancel, liters cancel, leaving you grams, and that turns out to equal 0.494. So if I needed to make, this is my pretty potently poisonous purple potassium permanganate. I needed to make 250 milliliters of a 0.0125 molar solution. I'm gonna go and I'm gonna weigh out 0.494 grams, and then I'm gonna put it into my flask, my volumetric flask. I'm gonna add water 2/3 full, swirl it, get it to dissolve, and then fill it up to the mark, okay? And this is the kind of calculation that I have to do all the time when I'm preparing for lab. So as I'm preparing your 0.1 molar silver nitrate solution for tomorrow's lab, okay, I have to go through and do this calculation. All right, so if everybody's going to use about 50 milliliters, we got 19 groups, so that's, 19 times 50 is going to equal, let's just say 20 times 50 is going to be 50 milliliters, that's 0.05. What am I going to need? A liter of it, whatever that turns out to be. My mental math here is hurting, okay? So I figure out, okay, I need to make that many milliliters of the solution. So then, okay, well, how many grams am I going to need total? And I buy it in 25 gram bottles. I got to make sure I have enough, okay? And so I do that. All right, I'm going to let you come back and do some of these other ones. This is going to be stoichiometry on these here, and we'll go from there. But I want to use the last few minutes to talk about.
So what we've done so far with the dilute one, the mold one, and stoichiometry, that's like all the AP chemistry.
Yeah, but again, on some of these, you have limiting reactant on the stoichiometry.
Yeah.
And those things, and we'll talk about some of that because you're gonna need to know on some of that as far as to do the lab calculations. But that'll be Wednesday, and we'll go over any last minute thing on that, and then Thursday will be the quest.
So all of these could be like on the.
Yes. Yeah, that's what I give it to you. And so we'll use between.
Okay.
All right. But now let's turn to the back page. The copy out of the textbook page. And we need to calculate different ways of measuring concentration. So we'll look at what number is that? 21. Hydrochloric acid is sold as a concentrate aqueous if the molarity is 12 molar. We have three other ways of calculating concentration. Now this is the part that is not on the AP test, so make sure we know that. It's going to be, but because you're going to need to know how to do all of these in college, I want to go over it. And then this is going to be bonus on the test. Okay? So I'm just as far as so we can put our priorities. So that's why I'm going to do it fast, and I'm only going to do it one time. So however much time you want to put into it to learn it is going to be on you. Okay? So we already know molarity, concentration. Number one is molarity. Capital M. And we already we've done that. That's moles of solute over liters of solution. Okay, that's the most common. That's the one that you need to know how to do, and we're good with that. But the second one is molality. And that's a little italicized M. And somebody in here remembered what that was. I thought it was Nathan, but it's moles of solute over what? Kilograms of solvent. Now make sure that we understand solvent. This is solution, this is solvent. Moles of solution, liters of solution versus kilograms of solvent. Okay? Two different things. So if I'm going to make a molal solution, I need to know exactly how much solvent I have, not the solution. Here we're adding enough water to make 250 milliliters of solution. With molality, I'm counting on, okay, I'm adding, if I add a liter, what's the density of water, by the way? 1. Okay, so if I'm adding a liter, I'm adding a kilogram. So this is say, okay, so I'm adding so many moles of solute to 1 kilogram of water. So now I'm measuring the exact amount of solvent. Here, molarity, add enough water to make how many solution. Molality, it's exact amount of solvent, but it's kilograms, not liters. Okay? The third one is mass percent, which is going to equal grams of solute over grams of solution, okay, times 100. And just to clarify, that means it's going to be grams of solute divided by grams of solute plus grams of solvent times 100. Now, just if we're doing ppm, does everybody know what ppm stands for?
Parts per meter.
Not meter, parts per
Mole.
parts per, not
Mass.
100, but parts per
Million.
million. ppm, that's another way of calculating concentration, is parts per million. Instead of multiplying, you go times a million instead of 100. Okay, so the only difference is you multiply by a million. In other words, the parts per million is so less concentrated, we need to multiply by a million rather than multiply by 100 to get a workable number. Otherwise, it would be 0.000000 something. Okay, and then if it was parts per trillion, PPT, what would we multiply by? Multiply by a trillion.
Even if you multiplied by a million, would you still write it as a percentage?
No, you'd say ppm. Okay, good question. The percent is always times 100, but it's if we're doing parts per million, you just multiply by a million in your answer, then the unit on your answer would just be ppm. Okay, and then lastly, we have mole fraction. And for some reason or other, they use mole fraction as an X. And that's equal to moles of solute. Now you can really do mole fraction either way over total moles. And I'm not going to write this one out. And it's a fraction, so we don't multiply by 100. It's just a fraction. But again, if grams of solution is grams of solute plus grams of solvent, total moles is going to be what? How do we get total moles?
Moles of solute equals moles of solvent.
Yeah, moles of solute plus moles of solvent. Okay, so if you need to write that out, you can write it out. But total moles is just going to be moles of solute plus moles of solvent. Sometimes we need to go the mole fraction of the solvent, and then it would just be moles of solvent on the top over total moles. Okay, so those are our 4 different ways of measuring concentration. So this whole problem is, how do we convert from one to the other? If I'm given one, how do I go to the others? And then the density is going to be your key on this. Okay? Because that's going to be a density is a conversion factor between what 2 things? Volume and mass. Mass volume. Grams over milliliters. Mass over volume. Right? That's how we're going to get from liters of solution to kilograms of solvent, or vice versa. Okay, that's how we're going to go from a volume to a mass. The density is going to be the key. Okay, now we don't need to take a break because we had that long break just when you were doing all the problems and y'all were playing on your computer and doing all that. Whoa. We need to finish this. Okay. Ah, crap.
Break time.
No. I gotta erase.
My dog was a belly break.
Y'all get a break, you go to lunch. I get to do this all over again.
You get paid to do this, Mr. Hobbs.
Okay, so hydrochloric acid, the thing that I'm given is solution if the molarity of the commercial acid is 12. So I know it's HCl is equal to 12 molar, which means that it's equal to 12 moles of HCl for every 1 liter of solution. Now, it's important for us to understand that that's what we know. 12 molar tells me it's 12 moles of HCl for every 1 liter of solution. So, the first thing I need to do is molality. Okay, well, molality, what do I need?
Kilogram.
I need kilograms of solvent. Okay? Now it tells me that the density, okay, the density, now most of the time it's the density, this is the solution. The HCl 12 molar solution, it has a density of 1.18. So if I take, so for A, I can say 1 liter, and let's just go 3 sig figs. 1 liter times, because it's exactly 1 liter, the molarity. Which is, well, 1 liter, because the density is in grams per cubic centimeter, 1 liter is how many cubic centimeters? 1,000. The cubic centimeter is the same as a milliliter. This is something that we need to know too. Make sure we know 1 centimeter cubed is equal to 1 milliliter. Therefore, 3 dots in a triangle, 1 liter equals 1,000 cubic centimeters. A 1,000 cubic centimeters. That's 3 dots in a triangle, mean therefore. You guys learned that math? Yeah. Okay, no. We learned it now, okay? That's just an abbreviation for therefore. That's not a testable thing. That's just my shortcut. Okay? So a cubic centimeter equals a milliliter. That needs to be something that you know. So therefore a liter is going to be 1,000 milliliters, 1,000 cubic centimeters. So I'm going to start with that. As 1,000 cubic centimeters times my density of 1.18 grams over 1 cubic centimeter. So, very challenging math here. That means that 1180 grams of solution. But do I want grams of solution for molality? What do I need? Grams of solvent. And what's the solution made up of though? Solute and solvent. So if I know that the solution, so 1180 grams of solution is equal to so many grams of solute plus so many grams of solvent, right? But obviously, if I'm gonna, this is what I need, how do I get this? Subtract, but I have to know, I can't have two variables. If this is my unknown, I've got to know this. How do I know this? Think about it again, my given. What do I know about my solution?
12 moles.
Of
HCl.
HCl. If I know moles, do I know grams?
Yes.
So I can say 12 moles of HCl times 35.45 plus 1, so it's 36.46. Somebody give me that number. Again, this is given.
437.5.
So 437.5 goes there. So now we can say grams of solvent is equal to 1,180 grams of solution minus 437.5 grams of HCl solute is equal to
742.5.
742.5 grams. The solvent is water, which is how many kilograms?
Wait, 742.
Are we done yet?
I gotta do that.
So now my molality is of HCl is going to equal, did the moles change? 12 moles over 0.7425 kilograms of water. And that equals,
16.16.
we would say 16.2 little m. That's the hardest part. Of all of this, that's the longest, hardest part. You now have everything you need to solve everything else. Okay? Now, if you're wondering about where any number came from, now's a good time to ask. Notice it's the density, but the mistake is that the density is the density of the solution. So we always have to keep track of solution, solute, and solvent. The moles is always going to be of the solute. In molarity, it's solution, but in molality, it's solvent. Okay? So we just got to keep those straight. So, again, we know the density tells me the mass of the solution. I have to get the grams of solute to subtract it, and then that gives me the kilograms of solvent, and then I can just plug it in. So now, okay, if I want to do part B simply says, what's the weight percent? Well, that's grams of solute. Do I know grams of solute?
Yeah.
Which is how much? What's my percent of solute? What's my grams of solute?
437.
437.5. What's my total mass of the solution? Not solvent, solution. 1180. Times 100. So my percent is going to equal
37.08.
so 37.1% HCl. So my concentrated HCl is 37% HCl. The rest is water. Okay? But that's a saturated solution. That's the max that can dissolve. That's as concentrated as it gets, which is why when I take the lid off, you start seeing smoke coming out, and you breathe it and it burns you because the HCl is maxed out in there, so it comes out of solution. HCl is a gas in its normal state. Now, this is not a question on here, but what's the mole fraction?
12.0.
Okay? What's the mole fraction? Well, we know most of everything. Okay? We need, what's the moles of solute? How many moles of solute? How many moles of HCl do we have? Okay? So X of HCl is going to equal 12 moles of HCl. We still know that. Over total moles, which is going to be 12 moles plus what? What else do we need to know? What's the mole fraction going to be?
Moles of the water.
Total moles, okay, which is going to be moles of solute and moles of solvent, which we need moles of water. What do we know? How many grams of water we have?
Yeah.
Yeah, we know 742.5. So how do I get moles of water?
Times 18.02.
Not well divided by. That equals
41.2.
41.2 moles of water. Okay? So that means I go 41.2 moles here. So keep it as a fraction. So somebody divide that out for me.
0.26.
That's my mole fraction. The X of HCl is 0.226. Okay, it's not a percent, it's just a mole fraction. So we use the density. Once we go, we can just go back and forth. The whole thing is you just have to know your what each one represents. What's on top, what's on bottom. And then you just go back and forth. Okay? Now I'm gonna look at one more. Number 24. Does everybody have all this down?
Yep.
Yeah, we have just a few minutes here. It's what do I have? What am I looking for? How do I get there? Okay? Again, this take the stress off, this is all bones. Okay? But it's good math. It's really just knowing what unit I have and how to convert to the other one. The density is the key to go from grams to liters and liters to grams. Okay? Alright. So let's look at 24, because 24 is confusing as far as what I'm given. I have 95% H2SO4. Okay? What is the and the density, and they always give you the density of H2SO4 is equal to 1.84 grams per cubic centimeter. That's my two givens right there. So what does it mean to say that I have 95% H2SO4? Means what?
The 95% is solid.
Okay? So I need to know, okay, so mass percent is grams of solute over grams of solution. So what goes on top, what would go on bottom here? How many grams, if it's 95% H2SO4, what is percent out of?
100.
100. So what can I say? What goes on top and what goes on bottom?
95 grams on top.
95 grams of H2SO4 is on top. Did you say that already?
Oh, yeah.
Over 100 grams of solution. That's my abbreviation for solution, by the way. Okay? So now when I say that, okay, what is the molality? Molality is going to equal what over what? Moles of H2SO4, solute, over kilograms of water. Because that's my solvent. Now, is there any way for me to get moles of H2SO4?
Yeah.
How?
You got molar mass.
Okay? The molar mass, right? So I can say that I have 95 grams. We'll just do 2 sig figs. And then the molar mass of this is going to be 1 mole over 98 point, it's 37, yes, it's 07 plus 209, 98.09 grams. Okay, so that's my moles of H2SO4 on top. Does everybody understand what I'm doing right there? We're just using the molar mass, converting that to moles rather than doing it separately. What about kilograms of water? Do I know how much kilograms of water I have?
Yeah. You know, 100 grams of water, right?
Do I have 100 grams of water?
No, minus the
5.
90. Yeah.
Say that again, Taylor, what?
5 grams.
I only have 5 grams of water because I have 100 grams of solution, but the solution is solute plus solvent. I have 95 grams of it is solute. So only 5 grams is left as solvent. So 5 grams to kilograms is 0.005. Let's go with one more sig fig because it's just 5.0. I'm just adding in sig figs just for fun. Okay, it's 0.005 basically. Okay, does everybody understand where the 5's coming from? If it's 100 grams of solution, 95 grams of it's H2SO4, that only means 5 grams must be water. It's almost pure H2SO4. So when we divide all that out, what do we get?
93.70.
93.7.
193.
0.93.
No,
You said
193.
193.7.
70, yeah.
And that's going to be molal. Look how concentrated that is. It's 18, well, let's just say, what's my molarity? What's the molarity? Well, molarity is equal to moles of H2SO4 S over liters of solution. Well, do I know moles of H2SO4? Okay. If you happen to have written this down, what did that inside the brackets equal? 0.9685. Okay, so you already had that calculation done, or you at least had it set up. So I know that this top number is 0.9685 moles of H2SO4. But how do I get liters of solution? I know I have 100 grams of solution, right? And I know the density is 1.84 grams per cubic centimeter. So liters of solution are going to equal 100 grams times, where does grams need to go? Does?
At the bottom.
1 cubic centimeter over 1.84 grams. Sixty-four point.
54.35.
So I'll say 4 cubic centimeters, okay? Which is equal to how many liters?
54.4 milliliters, so 0.0544 liters.
So I can plug that into here. So my concentrated sulfuric acid that I used the other, I had out here, and that we used to talk about is about 18 molar. 95%, we say it's 18 molar. Now, it doesn't ask for this, but we could do mole fraction too, right? Because now we know how many moles of H2SO4. We know the total mass of my solution is 100 grams. Okay, so I know I have 5 grams of water. So I can figure out how many moles of water I have. I can get moles of solute over total moles and get my mole fraction. Okay? So it's just kind of going back and forth, back and forth. What am I given? What am I looking for? Everybody's gonna get a bonus point, bonus points. So that means that if this quiz is, what did I say, out of 50 points? Okay, we can get 55 out of 50. Everybody's gonna make 55 out of 50. Yeah, sure.
My dog is off.
Yeah, I saw that. All right. Now, in our last 4 minutes,
We're gonna sit here.
no, why don't we?
Why would you start breaking?
You don't need a break. You get a whole, you get so much break next week.
Bro, why'd you cut my dog, bro? We're going against.
Let's see if you can in 4 minutes do number 6. 4 minutes, number 6, okay? And you can, all right, go Jags, and we'll talk about this on Wednesday when we come back.